Webcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. I'm Woody Cash, the SCT Content Knowledge Officer for the Golden Gate Chapter. Welcome to the Golden Gate Chapter's webinar, Understanding HFC Plant Power Supplies. Before we get into the webinar, just to go through a little chapter business. Elections were completed at the end of Q4 2024. So please check our website. You'll see the new officers listed there, and always feel free to reach out to us if you need anything. On March 4th is our next webinar, OTDR webinar, OTDR functions and measurements with Pete Zarelli of VX. Pete did a webinar for us last year, very informative, so we asked him to come back and repeat that. On April 23rd is our annual Vendors Day. Please note, it has changed locations. This year it's going to be at the DoubleTree in Pleasanton. And I do believe we have a golf tournament on the 22nd. So those events are coming up. Just a reminder, if you have any training topics you would like to see presented in 2025, please email them to me. That's wfcash@comcast.net. So I'll take a minute just try to plug the SCTE. Again, if you're not a member, please sign up. If you are, and I believe all Comcast and all charter employees are full access members, so it's free to you to go in and sign up. And then as long as you click into the website once or twice a year, you will get an automatic renewal and don't have to re-enroll every year. So make sure you visit our website. And the great thing about that is we have loads of training, anything from primer training, which are just like 10-minute sessions, to full courses. So so please take a look and go around our website and familiarize yourself with the training, or I should say SCT.org website. And in addition, if you need more information about Vendors Day, it's all listed on our website, so please check it out. So let's get into understanding HFC power supplies. While you may not think of power supplies as cutting-edge technology, they are key elements to our network. Without reliable power, the network will not perform or will greatly underperform. For today, we'll cover the following aspects. So AC/DC power, power supply functions, power supply alarms, and troubleshooting tips. Today's printer is George Bosak. George is a senior technical representative for EnerSys. So I'm going to turn it over to George. And oh, by the way, we have 3 polling questions that I'll put out to you guys for some interactivity and give you a chance to check your knowledge. So with that, I'll turn it over to George. And then George, just a reminder, take a minute and pause occasionally, and I'll get these out. If not, I'll try to monitor and see that. Also, for the attendees, please put any questions you have in the questions box. I will pause George and try to read those out. He would like to get them as he goes along and not hold them to the end. So thank you, everybody.
And thank you, Woody. And like Woody said, you take advantage of the SCT training. You know, if you're not a member, join the SCT. If you are a member, utilize all the information that the SCT has to offer. I've been an SCT member for, I don't even know how many years now. I think I joined in 1993, so it's been a while, and it has been a very good organization to be a part of. So with that, I'll get started on get a little training on outside plant power supplies. First slide I got up here is the most important slide that I do in any of my training, and that is basically a safety slide. Power supplies, of course, work on electricity. You know, if you come in contact with electricity, it is possible that you can get injured or even potentially killed. So when you're working with AC and or DC, always follow your company's safety policies, use the required PPE. You want to be safe throughout the day. You don't want harm to come to you. You don't want harm to come to others. If you don't understand the equipment that you're working with, ask somebody to provide training before using the equipment, and preferably to get really good understanding of how equipment and tools work, ask the person that is training you on that equipment to give you a demonstration of how it works. Don't use your body to test for foreign voltage. We have tools to do that. There are a lot of conductors out there that are not supposed to be energized, but there is a potential that they can be energized. So use a foreign voltage detector, use a voltometer, wear your gloves, use devices to test for that foreign voltage. Don't be using your body to find out if it's hot or not. And then, like Woody said, during the training, I encourage questions in this format. It's best if you maybe type those questions into the chat, and then Woody will stop me occasionally and ask me the questions. So also with safety, we work up close to the power lines. You want to make sure you maintain a safe working distance from the power lines. I don't have the National Electrical Safety Code safe working minimum distances from different voltages on this chart. I used to have it on here. I took it off because really what I want technicians to understand is you don't know what the voltages generally are up on those power lines. So stay as far away from the power lines as you possibly can. And never move power lines on your own. If you have any power lines that seem to be in your way or need to be moved or anything, get the power company out there and have them move them. And then, of course, remember to follow your company's safety policies as far as setting up a safe working zone and use your PPE. You want to be as visible as possible out there today. Now, if you're parking alongside the road, make sure your cones are out, signage is out, use your lights, and again, don't forget to use your, the PPE that's required for that job. Power supplies and batteries are heavy. Sometimes I work with technicians who haven't lifted power supplies or batteries. They don't realize how heavy they can potentially be. You want to use proper lifting techniques and proper carrying techniques when you're working with power supplies and batteries. Power supplies, the heaviest power supply I have seen is been 95 pounds. That's a pretty good chunk of weight. And then batteries now, we have outside plant batteries that can weigh as much as 145 pounds each. So, when you're out there working them, be careful again when lifting and carrying power supplies and batteries. Like I mentioned before, you want to make sure you understand how your tools and equipment work. You want to be safe with them, and you want to be effective with them. The better you understand your equipment and your tools, again, the more effective you will be in your job, and the safer you're going to perform your job. Check your tools and equipment daily for damage. If there's damage to leads or anything, have those repaired or replaced. Check the batteries in your test gear. Weak batteries can cause incorrect readings, especially on voltmeters. I've seen technicians before who have been out troubleshooting issues on the plant. Their voltmeter was giving them strange readings, and they're kind of chasing their tail, and they find out that their batteries are basically bad in their voltmeter. And like I said, if you don't understand how a piece of equipment works or a tool works, ask your technical trainer, ask your supervisor, ask somebody to provide training, and again, preferably give you a demonstration of exactly how it works. I've got a few different items up on the screen here. I have a voltmeter. We recommend that you use a true RMS voltmeter when you're measuring the AC voltage on the coaxial portion of your cable plant. I'll get into why that is a little bit later. I have an amp clamp showing up there. We'll talk about how an amp clamp actually functions. It seems that's probably one of the pieces of equipment that I see that a large majority of technicians do not understand. I've got the foreign voltage detector there. I've got a conductance meter with a temp probe, and then insulated tools. If possible, when working with batteries, you want to use tools that are insulated. So let's go over a little bit about some basic AC/DC. Maybe some of this stuff you have learned in the past, maybe you're new to this, but let's go over a little bit about what some of these terms actually mean and what they are. So voltage. We talk about voltage all the time. What actually is voltage? Well, voltage is actually electromotive force. Voltage is a difference in potential. You don't get shocked unless there is a difference in potential. I always have kind of a tough time explaining that difference in potential to some people. Maybe one of the best ways to explain it is I'm walking across the living room on a piece of carpet, maybe shag carpet. And as I walk, I kind of scuff my feet. When I'm doing that, my body tends to build up electrons and I gain electrons. When I walk over to the door, that door handle doesn't have as many electrons as my body has. So I have a difference in potential than the door handle does. When I touch the door handle, I release those electrons into the door to equalize them out. Voltage is pressure. So to get electricity to move through a wire and go a distance, you have to have pressure, and that's what the voltage is. The higher the voltage, the farther the electricity will travel. In your coaxial cable plant, 90 volts will travel farther than 60 volts. The power company doesn't produce 120 volts at the power station, at the power generation station, and push it to your house. It would never make it. So they produce a high voltage at the power station. Actually, they step it up to a high voltage, and then they push it long distances. And then when it gets to where they're going to use it, they step the voltage down. So voltage is pressure. Current is the flow of electrons. So I'm going to get my laser pointer here. The electrons are the little guys that are flying around my atom over here, kind of to the right center of the screen. So in the center, I have protons and neutrons. That's my nucleus. And then around my nucleus, I have electrons flying. So this is my representation of an atom. And of course, everything is made of atoms, right? So current is these little electrons here, one or more of these electrons, moving from one atom to another atom, to another atom, to another atom, to another atom. To get electricity to work, we have to have electrons that are moving through a conductor from atom to atom to atom. And when we have that, we have a flow of electrons, and we call that a current. Resistance. What is resistance? Well, resistance really comes down to how easy is it for me to move those electrons from atom to atom to atom. So like I said, everything's made of atoms, correct? Some things electricity will move through and some things electricity won't move through. So conductors. Conductors are elements where you can get those electrons to move from atom to atom to atom. The best conductors in order are silver, followed by copper, gold, and aluminum. Gold is not the best, but gold is the only one that doesn't tarnish, at least out of those four that doesn't tarnish. So that's why we like to use gold for connectors and things that we don't want to basically corrode. Copper is a very good conductor, and we use it mainly because it's relatively inexpensive compared to silver and gold, and it doesn't corrode nearly as fast as aluminum does. Copper actually has a free electron that will move by itself from atom to atom to atom, but they just randomly move around, so they really can't be used for power unless you have a voltage applied to them to push them all in one direction. Insulators are elements where the electrons don't move from atom to atom to atom. So best insulators in order: rubber, glass, pure water, and oil. So in rubber, for example, you can't get the electrons to move from one atom to another atom to another atom. Electricity doesn't flow through rubber, so it's a very good insulator. Resistance also comes down to temperature. Is it hot or is it cold? The hotter it gets, the more random electron movements become, the more they tend to crash into each other in an element, the more resistance that builds up. So your cable plant is more efficient as far as power is concerned on a day when it is cold compared to a day when it is hot. Power. What is power? Well, power is watts. And what are watts? Well, watts are the amount of energy that are consumed or produced by an electronic device. All electronic devices are rated in watts. If I go to Home Depot and I'm going to buy a heater for my house, maybe I'm going to buy a 2,000 watt heater. So anything that's electronic is going to be rated in watts. And how do I get watts? Well, or power? Well, if I take voltage times current, I end up with power or watts. So I have some laws here. I have Ohm's law, I have Watt's law. Watt's law example, P equals I times E. So if I have 120 volts and it's drawing 1.2 amps, that's 144 watts. If I change that and I had 12 volts, it would be 12 amps, and that again would be 144 watts. As my voltage changes, my current tends to change with it. So in an electronic circuit, if I raise my voltage, my current will tend to drop down. If I decrease my voltage, my current will tend to rise. What's with the different little letters and stuff? You know, why is it PIE instead of V, or I'm sorry, WCV? Well, if you look at it, voltage is actually electromotive force, okay? So that's what voltage actually is. So that's why the E. Current is actually the intensity of the electrons. So that's why I. Of course, resistance is R. And then watts are actually power. So that's why the P. Okay? So how do I force the electrons to move through a conductor? So what type of pressure, or how do I get these electrons to move from atom to atom to atom, like I said that they do when it's in electricity? Well, really, there are two ways that we basically do that. There are other ways, but these are the main two ways. So on the left side of the screen, I have a magnet, North Pole, South Pole. It's contained inside of kind of a tube. And then I have a copper coil on one side of that that's connected to a light bulb through conductors. Magnetic energy can force electrons to move in a conductor. And my conductor in this case is going to be copper. Copper has free electrons, so I can really easily move those electrons with the magnetic flux. So the strongest point of the magnets are the North Pole and the South Pole. Right now, the magnetic flux is not pointed into the copper winding. So my light bulb isn't lit up, the electrons aren't moving. I'm going to turn this generator on. This is what this is. This is a generator. I'm going to turn this generator on in a moment here. And as the North Pole starts to move into the copper windings, the electrons will start to move. And a voltage will start to build up. The further or the straighter that the magnet gets into the copper winding, the higher the voltage will get. As the magnet starts to come out of the copper winding, the voltage will start to go back down. And then when the South Pole comes around and goes through it, the voltage wave will go the other direction. So let's turn on my generator here. And the magnet starts to spin. And as the magnet spins through the copper windings, the electrons move. And you can see I get this funny little waveform coming out of my generator called a sine wave, going North Pole, South Pole, North Pole, South Pole, North Pole, South Pole. So this is a generator. This is what all generators that produce AC electricity basically consist of: magnets that spin past copper windings. You know, you might think of a wind turbine. That's pretty easy to figure out. The wind turbine spins the magnets that pass past the copper windings. You know, at a coal-fired power plant, well, how do they use coal to produce electricity? Well, the coal actually just is burned to heat up water. The water turns to steam. The steam sprays on a turbine. The turbine spins the magnets. The magnets go past the copper windings. Nuclear energy, basically the same. They use the nuclear reaction to heat water up to produce steam to spray on a turbine that spins magnets. So this would not be a very efficient generator, but if you built one like this, you could generate some electricity. Now, because I'm going North Pole, South Pole, North Pole, South Pole, again, my electrons are going back and forth. My waveform is going North Pole, South Pole. This is AC. This is alternating current. On the right side of the screen, I have an anode and a cathode immersed in an electrolyte. This is a battery, okay? Now, in my case here, I've charged the battery up. So generally, when you build a battery, so if you're at a factory and you're building a battery, let's say we're building a lead acid battery, we're gonna have a plastic container. In that plastic container, we're gonna put two different types of lead. We're gonna put the anode and the cathode. Maybe it's lead oxide and lead dioxide, okay? Now, when I put those lead plates into the enclosure, I'm going to put an electrolyte in there. For my electrolyte, let's say I use diluted sulfuric acid. And when I put those lead plates in there, those lead plates are going to have approximately the same amount of electrons and atoms on each plate, okay? I need to get a difference in potential in order for my battery to work. So instead of my light bulb circuit here, I would hook up a battery charger. The battery charger would basically force electrons and atoms from the cathode side, from the lead on the cathode side, to move through the electrolyte over to the anode side. Okay, so and what does that is the electricity from the power grid actually, you know, when I apply the electricity to my lead plates with the electrolyte, a chemical reaction occurs within the battery, and those electrons move through the electrolyte from the cathode to the anode. Now, once they get over to the anode, they kind of get stuck, okay? But now I have a difference in potential, right? And remember, a difference in potential is voltage. So now I have a voltage that is built up. Now, if I want to discharge my battery, the electrons, like I said, they have a tough time getting back to the electrolyte. The ions can move through my electrolyte here, but the electrons can't. The electrons have to move through an external path. So if I turn on my light switch here, or my switch, I should say, you can see that the electrons are forced to move through my light bulb. And as they flow through my light bulb, it lights the light bulb up. Now, once I get basically the same amount of electrons and atoms on each side on the anode and the cathode again, there is no difference in potential, and the battery is now considered dead. If I had a rechargeable battery, I would hook it up to a charger, the chemical reaction would occur, and I would move those electrons and ions from the cathode back to the anode side. This is DC. This is direct current. Okay. So direct current means the electrons always flow in one direction. So if I have a 120 volt battery here and it's fully charged, that means I have a difference in potential. I have more potential on my negative side than the positive side. When I hook up my light bulb, the electrons are going to flow out of the negative side through the conductor, through my load, in this case an incandescent light bulb, and then back to the positive side. Again, once they equalize out and I have the same amount of electrons on both sides, basically, my battery has no longer has a difference in potential and is dead, and the light bulb will stop working. DC has no frequency. If you look at DC like on a waveform monitor or a scope, it will be just a flat line. AC is alternating current. Like I said, I spin my magnet past my copper coils. As the magnet spins past the copper coils, the electrons tend to kind of jiggle back and forth, and the resistance in the filament the resistance caused by the filament causes the light bulb to heat up and glow, just like it does in the DC circuit. AC does have a frequency. Commercial power here in the United States is 60 cycles per second, 60 hertz, okay? In the HFC system or the broadband system, we work with frequencies, right? Your coaxial plan has frequencies starting at 2 megahertz. That's 2 million cycles. I'm sorry, correction, 5 megahertz. That's 5 million cycles per second, not 2, 5 million cycles per second, 5 megahertz. And we go up to, in some cases, 1.2, maybe 1.8 gigahertz. So if it's 1.2 gigahertz, that would be 1,200 million cycles per second. So RF radio frequencies are very, very high frequencies. Power is 60 hertz. It's a very low frequency. I got a couple questions on the screen here. Which light bulb will appear to be brighter? Okay, well, I got a 120 volt battery and I have a generator that's producing a peak voltage of 120 volts. So which light bulb would appear to be brighter? Well, remember the DC is always 120 volts going through my light bulb. So it's consistently 120 volts. The AC down here, my generator is going from 0 volts up to 120, back to 0 volts, back to 120, back to 0 volts. So it's going back and forth like that. The DC one would appear to be brighter than the AC one in this example. Other question I have here, what surrounds anything that is energized by electricity but you can't see it? Well, anytime you put electricity on a conductor and it's flowing through the conductor, you will have a magnetic field around that conductor. If it's DC, the magnetic field is static, meaning it engulfs the wire and it just kind of sits there. If it's AC, because the electrons are moving back and forth, my magnetic field will constantly change. Basically like it's doing as I'm producing electricity, North Pole, South Pole, North Pole, South Pole. So around all electric wires and anything that's energized, there is always going to be a magnetic field. RMS. So I mentioned earlier that we recommend that you use a true RMS voltmeter when you're measuring the voltage on your cable plant. So, what is RMS? Well, RMS just stands for root mean squared, and root mean squared is actually just a mathematical calculation to determine how much of a certain amount of AC equals a certain amount of DC. Okay, so DC is constant, 120 volts all the time here on my DC side, but on the AC side, it's all over the place, right? 0 volts going to 170, maybe 120, maybe 60 volts, right? It's constantly changing. So it's really hard to figure out exactly what I have on an AC side or in an AC circuit because the voltage is always changing. So I use this mathematical equation, and this mathematical equation tells me that if I want the same amount of energy in an AC circuit, I have to produce a peak voltage of 170 volts to equate to the same amount of energy I would have on a 120 volt DC circuit. So if you remember back to my generator and my battery, right? I had the 120 volt battery and I had the 120 volt peak generator. If I wanted my light bulb that was connected to the generator to be the same brightness as my 120 volt battery, my generator would have to produce a peak voltage of 170 volts. And then the two would be equal. So RMS, again, is just a mathematical calculation to figure out how much AC is required to equate to a certain amount of DC. That's really what it is. Cool. And I'll explain later why we want you to use a true RMS voltmeter on your cable plant. A little bit different reason. So we abide by the National Electrical Safety Code and the National Electric Code. The National Electrical Safety Code tells us we need to keep our cable lines away from power lines, right? Pole to pole, when we're running parallel to power lines, we're supposed to say minimum 40 inches. And that, in some jurisdictions that may be increased. It may be actually a greater distance, but minimum is 40 inches. Pole to premise. So how far is your drop supposed to stay away from the service line when you're running from distribution or from your plant to the premise? Should be 12 inches. When technicians are wiring homes and they're running parallel with a power line inside the house, they should stay a minimum of 2.5 inches away from that power line. So why stay away from the power lines? Well, there's a few reasons. One is if my guy's up in the bucket truck here working close to the power lines, if he was too close to them, he could potentially touch them, which could cause harm or even potentially death to come to him, right? So we don't want to be close enough that we could inadvertently touch the power lines. Sometimes technicians will say, well, power can arc or jump. That is true. If you are, very well grounded and you get close enough to the power lines, it is possible for it to arc from the power lines to you, which would not be a good thing. Really, the main reasons we stay away from the power lines when running parallel with them is because of an effect called electromagnetic induction. Remember, to produce AC electricity, I move a magnetic field back and forth across a conductor, right? Well, your strand is a conductor, right? It's steel. And your coaxial cable plant is a conductor, it's aluminum, right? So if I take my cable line here and I move it up too close to the power lines, and I get within the changing magnetic field of the power lines, that changing magnetic field going north pole, south pole across my strand and my aluminum will actually cause the electrons in my strand and my aluminum to start to move, and I will actually energize my cable plant because of the magnetic field that is being produced by the power lines. So you always want to keep distance between you and the power lines, even when you do joint trench underground. So if the power company opens a trench and you're going to go joint trench with them, power lines go in. The next thing that should go in is some fill dirt, 12 to 18 inches, and then the cable lines should go in. Don't throw the cable lines right on top of the power lines. So what is electromagnetic induction? Electromagnetic induction is basically the process of inducing a voltage and a current onto a non-energized conductor using the changing magnetic field produced by an energized conductor.
I do have a question, George.
Sure.
So how is, this comes from Maurice. So how is Romex explained when it's less than 2.5 inches?
How is Romex explained? Well, it's
I,
less
this,
than.
I think I think what Maurice is saying is you go into a home and you see the Romex like right next to where the where the cable drop is, or yeah, inside
It's not.
wiring.
It really shouldn't be. Like if you're doing a 2x4, it should be on the opposite side of the 2x4. If you're running parallel through an attic, when I was in the operation side, I was a technical training manager. I worked quality assurance, and technicians, even though they were trained not to, a lot of times would zip tie to like Romax. They would zip tie to the mast coming down, the side of the house. Really not supposed to do that. But unfortunately, a lot of times, technicians find that the easiest way to do. And of course, contractors that are building houses, generally they don't know that. They're just putting in a piece of wire, and they don't know that they're supposed to stay away. Now, the good thing is, induction doesn't happen as bad at low voltages than at high voltages. So the higher the voltage, the greater magnetic field, the more likely you are to have induction. So if you do get your cable lines close to the power lines within the premise, the amount of induction you have is going to be limited, but you definitely don't want to do it a lot and have be in parallel with those power lines, or zip tie or anything to like them. Again, usually when I see them too close, it's because either the technician didn't understand that, or the contractor, who again is building the house really doesn't understand that process can occur. So you may see it, but it really shouldn't happen. Again, the good part is the amount of induction you're going to get is going to be minimal at those low voltages. Hopefully that answers his question.
Thank you, George.
Yeah. All right. So on this screen here, I have a 1200 volt generator, and I have a 120 volt light bulb. Now, if I hook my 1200 volt generator up to my 120 volt light bulb directly, my light bulb's not going to last too long, right? It's basically going to explode. But I want to use my generator with my light bulb. So how can I use my 1200 volt generator with my 120 volt light bulb? Well, what I have to do is I have to put a device in between the two called a step down transformer. So let's talk a little bit about how a transformer works. A transformer is an inductive device. An inductive device is a device that uses a magnetic field to function, basically. We see transformers all over the place, right? The power company has them on the poles by the premise. Generally, those are going to be step-down transformers. There are step-up transformers. Most of the time, you're going to see step-up transformers like at a substation or at the power plant. Most of the ones we see are going to be step-down. So how does a transformer work? Well, a transformer works by using the magnetic field produced by a primary winding to induce a voltage and current into a secondary winding, okay? So I'm going to start my generator up here. And as I do, my magnet spins past my copper coil. That causes the electrons in my copper to move back and forth, back and forth. My electricity flows from my generator to my primary winding, where it goes back and forth, because it's alternating, right? My primary winding is a whole bunch of copper wire wound up, all right? Now, to produce or to build an efficient generator, I actually have to do a couple things. I have to wind the wire up. Now remember, along a copper, an energized conductor is a magnetic field. Well, if I take all that copper wire and I wind it up, I can compress that magnetic energy into a confined area, basically, and I can make it very, very strong. And I want to have a strong magnet for a transformer. So I wind up all that copper wire. The other thing I have to do is I have to wind that copper wire around a steel core. Now, the copper doesn't physically touch the steel. There's some kind of an insulation between the copper and the steel, because I don't want the electricity to go through the steel core. I want the magnetic energy that is produced by that winding to flow through the steel core. Air is not an efficient way to move a magnetic field, but steel is an efficient way to move a magnetic field. So again, I start my generator up, 1200 volts goes into my primary winding. The energy, the electricity is going back and forth, back and forth. That produces a magnetic field in my primary winding. That magnetic field flows through the steel and it goes back and forth across my secondary winding. That secondary winding, that magnetic field going past that secondary winding causes the electrons to start moving in that copper wire back and forth, also produces a magnetic field. And because I have more copper on the primary side and less copper on the secondary side, my voltage drops from 1200 volts down to 120 volts, all being done using the magnetic energy that is produced by the primary winding. So no electricity flows from the primary to the secondary. It's the magnetic field that is flowing through the steel core that causes the electrons to start to flow in the secondary winding. Hopefully that kind of makes sense. I know it's a little bit complex, but this is how a basic step-down transformer functions. And most of the transformers that you see that the power company has are going to be very similar to this type of a transformer. This is a linear transformer. What I mean by that is that if this generator would happen to spike up to 1500 volts, my light bulb would go up to 150. If the generator would come down to 1000 volts, the light bulb would come down to 100 volts. So it's proportional as far as the change is concerned. Question I have down below, is the voltage provided by the utility company always constant? The answer to that is no. As the load on the power grid changes, the voltage will change. What I mean by load is the amount of current that's being drawn on the power grid. So as people turn things on and off, that causes the amount of current to go up and down. And remember, I said when the current when the voltage, or I should say, when the current goes up, the voltage comes down. When the current comes down, the voltage goes up. Think about sitting in your house in the summertime with all the lights on and the air conditioner kicks on. When the air conditioner kicks on, it requires a lot of current to start. So when it draws in all that current, the current goes up and it drags the voltage down and your lights tend to dim. Okay? So this is a simplified drawing of how a step-down transformer would work. So I mentioned earlier that we recommend use a true RMS voltmeter on your cable plant. The reason is because the non-RMS voltmeters are only designed basically made to measure a sine wave. So this wave that's up in the upper left side here, that's the waveform that's produced by an AC generator, right? I showed you that earlier, how that's produced. Pretty much anybody that works with electricity is going to be measuring this waveform. So if you're an electrician, you're going to be working with sine waves. If you're a pyro guy, you're going to be working with sine waves. Now, when I hook my non-RMS and my RMS up to that sine wave, they both measure approximately the same. They're a little bit different, but not that much. They're within a volt of each other. Okay, so you might think, well, what's the difference? Why can't I use a non-RMS voltmeter on my cable plant? Well, your cable plant doesn't have sine waves on it. The power supplies that you use take in that sine wave from the utility company, and they change the waveform to what's called a quasi-square wave when they're running in line mode. So when we're running off of the commercial power, we take that sine wave into the power supply, and we convert it to a quasi-square wave to put out on the cable plant. Now remember, those little non-RMS voltmeters, I should just say those non-RMS voltmeters, are not designed to measure anything but sine waves. So when I hook up a quasi-square wave to it, it basically gets confused and gives me an incorrect measurement. In this case, significantly higher than it actually is. So if you're out there troubleshooting a problem in your cable plant, for example, you have an amplifier that's not working, and the minimum input voltage for that amplifier is 50 volts. That's what it has to be, right? You take your non-RMS voltmeter and you measure the input to that amplifier and it says 52 volts. Well, you think you've got enough voltage for that amplifier to work, but in reality, you've only got about 46 volts going into the amplifier and it's never going to turn on. Now on newer power supplies, when we activate the batteries, I should say all older power supplies, are going to be quasi-square waves when they're running in line mode and when they're running in standby mode. But the newer power supplies, some of them, when you turn on or activate the batteries and you're running off the batteries, the output waveform is changed from the quasi-square to a modified square. When you measure a modified square with a non-RMS voltmeter, you'll notice that the measurement is lower than it actually is. So, you know, I'm not saying you have to use a true RMS voltmeter on your cable plant. I'm saying if you don't use a true RMS voltmeter on your cable plant, you better understand how those different waveforms affect your non-RMS voltmeter. Just a little bit of you know, why the square top wave. So, you know, why the flat wave? Do we use that on your cable plant? Short answer is efficiency. More efficient for power in your cable plant. Don't have quite enough time to go into that in detail today, but more efficient using that quasi-square or that modified square compared to using a sine wave. Amp clamp. So like I said, amp clamp is one of the tools that I see a lot of technicians get that they don't understand. An amp clamp is an inductive device. Underneath the clamp part is steel. So when I clamp my amp clamp around an energized conductor, the magnetic field that is produced by the energized conductor is picked up by that steel that's under the clamp. And then the components within the meter with the amp clamp convert that magnetic energy that is detected into the amount of current that's flowing through the energized conductor. Okay, so I got a power supply here and it says my input current is 11.8 amps. I put my amp clamp around the cord going to the power supply, but it says 0. Well, how can that be? Shouldn't there be, or you know, shouldn't there be a magnetic field around this cord that this amp clamp picks up? Well, how many energized conductors are required to complete a circuit? The answer is a minimum of 2. Okay, so when I put my amp clamp around the cord, I kind of split the jacket here so you can see the wires inside of my cord here, right? This is my cord feeding my power supply. There are going to be 3 conductors inside of there, right? 2 of them are going to be energized, the white and the black. And when I put my amp clamp around all these wires at the same time, or just around the white and the black, the magnetic fields are going to cancel each other out because one is positive, one is negative. And when you would put a positive and a negative together, they cancel each other out. So the correct way, and don't strip your cords back to do this, I'm just doing this to show you the correct way to measure current is to only put around your amp clamp around one energized conductor. So if I put my amp clamp around the black wire, it says my power supply is drawing 11.8 amps. If I put it around just the white wire, 11.8 amps. There is current flowing on the neutral, right? There has to be. It's a AC circuit, so you have to use both the positive and the negative. If I put my amp clamp around the green wire, it better be 0. There should never be any current flowing to ground. If you put your amp clamp around the green wire and you show current on there, get a hold of an electrician to find out what's wrong with the wiring in your facility. So I can use my amp clamp to measure the amount of current that is being drawn from my power supply by putting it around the wires that come off of the alt box or the SPI that go to the power supply, correct? Some guys have done this and they notice that it's sometimes different between the white and the black. Now, normally, if everything is working exactly correct, and I put my clamp around the black wire, it says 5.15 amps in this case. The white wire should have the same amount. So why is sometimes the black different than the white? Well, remember the white is your neutral, okay? That is the shielding of your cable plant, so to speak. That shielding of your cable plant connects to the back of this SPI on the housing of the enclosure. And what sometimes can happen is the current on the return doesn't make its way all the way through the power supply, and it takes the path of the housing of the enclosure to get back to the electricity. Because remember, the housing is tied to the shielding, it's tied to the SPI, it's all tied together. So sometimes some of the return current will actually flow through the enclosure back to the electrical panel or the breaker box instead of flowing through the white wire. So if you're using your amp clamp to measure the amount of current from your power supply, I recommend always using the black because in that case, it can only flow through the black wire to get onto the center conductor. So it will be the more accurate of the two for sure. How about using an amp cap clamp on your cable plant? Can I just clamp it around the coaxial cable? Well, no. Remember, your coaxial cable is two energized conductors. The center conductor is the hot, and the jacket, or I'm sorry, not the jacket, the shield is the neutral, right? So if I throw my amp clamp around a coaxial cable, you might think it should show up 0 down here, because remember, there's two magnetic fields, right? From the center conductor and from the shield. Well, the thing about coaxial cable is, remember, one energized conductor is shielding the other energized conductor. So the magnetic fields don't always cancel. So sometimes when you throw your amp clamp around a coaxial cable, it will show you current flow. The thing is, it's not correct. It's going to be off. The only way that you can accurately measure the amount of current flowing through your coaxial plant is to separate the center conductor from the shield. And the only good way that I know how to do that is to take the faceplate out, like I'm showing on the right-hand side here. Use some alligator clips. Make sure that you have insulated clips. Make sure you are wearing your gloves and that you're being safe when you're doing this, because your plant is going to be active when you do this, right? So if I take my faceplate out and I put a clip from the power source to the other pin, now I have separated my center conductor, which is my alligator clamp connection here. I've separated my center conductor, or my hot wire, from my neutral, which is my housing and my shield. You have to have a complete circuit for current to flow. Some guys, you know, I've asked them before, well, how do you separate your center conductor from your shield? And they'll say, well, core back the shield. Well, if I do that, I no longer have a complete circuit and current is not going to flow. So in this case, I do have a complete circuit. Current is flowing through my center conductor, and my amp clamp is telling me I have 8.71 amps of current flowing down the left side. Now, some guys also said, well, if I do this, it's going to cause an outage. Well, the only time you're going to do something like this is when you're out there tracking a problem, and the problem that you're tracking in this case is probably going to be a short or an overload, which means you already have an outage. Foreign voltage detector. So I mentioned that, you know, anything that's metal has the potential to be energized. Anything that's metal is a potential conductor. So, you know, when you're out there and you're getting to work, ready to work on your cable plant, again, wear your gloves, but also use your foreign voltage detector to check those metal components to see if there is any voltage or current strain on those. Foreign voltage detector is an inductive device also. So what it's actually looking for, it's looking for a magnetic field, a changing magnetic field generally, because most foreign voltage detectors will only do AC, they won't do DC. So in this case, my foreign voltage detector, I don't even have to touch the down guide, just get close to it. It goes off because it's detecting the magnetic field that is engulfing the down guide, because it is energized. Shouldn't be, but it is. I don't have in this presentation, but if I wanted to see exactly how much voltage on this, I could take my voltmeter, touch my voltmeter to the down guide, and then establish a ground, you know, a different ground, and connect my voltmeter to the down guide. I generally can't use the ground wire that's on the pole, because that one is going to be bonded to everything else. So again, there would be no difference in potential. I have to establish my own ground to check for that difference in potential. Conductance meters. So conductance meters are generally used, or well, I shouldn't say generally, conductance meters are used to test batteries. We'll talk a little bit more about batteries later, but voltage should be tested on your batteries, but voltage doesn't generally tell you if your batteries can carry a load. This device can. If you have one of these devices, I definitely recommend using it. It's a very good way to test the batteries. The only number you really care about is this S number here. That's the Siemens number of the battery. And what you have to know is what the manufacturer's specifications are for replacement value, really. The other numbers, the voltage, it's useful. This number here, which battery number, doesn't really matter. The reference means nothing at all unless you have actually gone into this meter and programmed specifically the battery type you were testing. Also, when you're using this meter, you want to shut the breaker off of your power supply. disconnect the batteries, and wait about a minute for them to stabilize. You don't have to disconnect the wires between the batteries when you're using this, and only test one battery at a time. If you put too much voltage into this meter, you're going to blow the fuse or blow the meter up. Unfortunately, I've seen technicians who have tried to test across the entire string before, and it trashes the meter. All right, so finally, let's talk about the power supply more. So the main purpose of a cable UPS or power supply is to provide very stable and clean power to the broadband system. So the power supply is used to keep the voltage on the cable plant stable, even when the voltage coming from the utility is not stable. So it does a few things though. That's the main purpose, but it also steps the voltage down, right? You have 120 volts or 240 volts coming from the utility. The National Electrical Safety Code requires that the voltage on your cable plant be less than 90 volts RMS, and it's important that we measure it at RMS, okay? So we have to step the voltage down from a higher voltage to a lower voltage. Less than 90 volts RMS is considered a low voltage, which is safer to work with than these high voltages. No voltage is safe, okay? I don't care what the voltage is, it's not safe. But 90 volts or 60 volts is safer than working with 120 or 240. Okay, so power comes in from the utility into the power supply. It goes into our transformer inside the power supply, which is a ferro-resonant transformer. The transformer used inside the power supply is different than that linear transformer I showed you earlier. Okay, so our transformer is a voltage regulator, basically. If the voltage coming from the power company is 100 volts, we give you 89 volts off in this case. If the power goes up to 110, we give you 89. If the power goes up to 120, we give you 89. The job of the transformer inside the power supply is to keep that voltage stable if the utility is changing. Okay, we step it down and we keep it stable. We also take some of that power that comes from the utility from that transformer and run it into our inverter. When we are running off of commercial power, the inverter is the battery charger, okay? So we're going to take some of the voltage from the utility, run it into the inverter to charge the batteries up. Also inside the inverter is a brain. Important to realize the brain of the power supply is actually powered by the batteries. Now, if you don't have the batteries hooked up, the brain is dead, but you still get information from the power supply. But one of the main functions of the brain of the power supply is to constantly watch the power coming in. Okay, the transformer is dumb. I told you, the power can change coming in and it'll keep it stable, but it does have specifications that it has to stay within. So for 120 volt power supply, for example, we want to see at least 90 volts, but no more than 130 volts, 38 volts coming from the utility. We want to see 60 hertz, plus or minus 3%. So the brain in the inverter, which is powered by the batteries, is always watching the power coming in to make sure it matches the specifications for the transformer. As long as it does, the brain just lets the transformer do his job of keeping the output voltage step down and stable. But if the voltage and the frequency coming in from the utility goes out of specifications for the transformer, the brain will actually activate the batteries. Because if the power coming in is not within specifications for the transformer, we can't guarantee the output, but we can with the batteries. So we kick on the batteries, we take the DC voltage, which in this case is three batteries wired in series, which will be approximately 36 volts, well, more like 38. And we'll run that DC voltage into the inverter. In the inverter, we will change the DC voltage to AC voltage, push it back into the transformer, step it up to push it out to the cable plant. Now, I'll talk about this later too, but one very important thing also is that when we do activate the batteries, we have to disconnect from the utility. There's a relay inside the power supply called a line isolation relay. Every time that we activate the batteries, every time the power supply connects to the batteries, it has to disconnect itself from the utility by opening the line isolation relay so that we do not backfeed power to the power company. They get a little upset when that happens. If that relay isn't working, you're going to get a line isolation alarm in the power supply, That means a line isolation alarm on the power supply means the power supply will not turn on the batteries. And the only fix for a line isolation relay is to replace the power supply. Woody, before I go further, I'll let you ask put up the survey question, the first one.
Okay, I'll get started in that in a second. I'm not too practiced, but with this task, but you should see on your screen in just a second a question. If everyone in the audience would take a second to try to answer this. So the question is, what is the main purpose of a standby power supply? You have 4 options. 1, to ensure a stable output voltage cable plant. 2, to send DC voltage through the plant to active devices. 3, to convert utility voltage to cable TV voltages. And 4, to ensure the inductive reactance of the utility matches. So we will, let's see here. Did I do this right? I don't see. Oh yeah, I see 19% voted, so we're moving along. Got 35% have voted. Give it a couple more minutes. Okay, we're up to 50% now and climbing, so we're still doing okay. Give it just a few more minutes, or 1 more minute.
All right. I see, Woody, somebody in the chat. I don't know if that was you. When I first started, we had some plant that was still using 30 volts. Yes, I remember those days. That was a long time ago.
And I had a comment, did you use your tongue to test at 30 volts? No, I did not. I did not ever use my tongue to test it, but I did see people, I think I did try one time putting my wet finger on it, and I said, nope, it's okay, I'll never do that again.
Yeah, I've made some mistakes in my career too. Probably the worst one I had was trying to put a back nut on a coaxial cable with the plant active at 90 volt, and I had my hand kind of over the center conductor pushing on the back nut, and the back nut slipped and went on, and it shoved the center conductor into the palm of my hand, which was not a good experience.
Oh,
so
no.
I definitely recommend not doing that.
Yeah, so I'm going to close the poll, and then let's see if I can remember how to share it. There we go. So let's see. So 74% answered to ensure a stable output voltage to the cable plant. And then 21% to send DC voltage to the active devices. And number 3, 5% to convert utility voltage to cable TV voltage, and 0% to ensure inductive reactance of the utility matches. So I think the majority got this question right. The main purpose of a power supply is to ensure stable output voltage to the cable plant. So thank you, everybody.
I'll comment on that quickly, Woody. So send DC voltage to the plant through the plant to the devices. We never send DC voltage to our cable plant through the coaxial plant. Now the devices do actually use DC, but we convert the AC to DC at the device. I have had actually, during my travels, I've had a couple technicians that thought that when we activate the batteries on the power supply, that they thought that we actually send DC through the cable plant, but we don't. We never. It's always AC cable flow or AC voltage flowing through the cable plant. And then the other one there is maybe I didn't word that answer correctly. To convert the utility voltage to cable TV voltage. Well, some people might argue that we're actually changing the sine wave to the modified or the quasi square wave, so they might try to argue that that's right, but really the main reason for using the power supply is to ensure a stable output to the cable plant, so it's not changing. We can't, the utility power, like I said, changes throughout the day. You might get 120 volts coming out of the outlet, you might get 109, you might get 129. So throughout the day, as the load changes, the voltage at the outlet can actually change. We can't have the voltage on the cable plant changing 20 or 30 volts throughout the day. That would cause massive problems for all our active devices. So the power supply's main purpose is to ensure that the voltage on the cable plant basically doesn't change throughout the day.
So thank you, everyone. I'll hide this and we'll continue on with our presentation. We do have two more questions and we'll get to those later.
All right. So on the screen here, I'll kind of run through this kind of quick. This is just a ferro-resonant transformer in a power supply. So just to kind of give you an idea of how things work. In my case, this case here, I got 124 volts AC flowing into my power supply. It's going through an electromagnetic interference filter. It goes through a MOV board. MOV stands for metal oxide varistor. That's a surge protector. Then into the line isolation relay that's connected to the brain of the power supply. Remember, the brain's always watching the power coming in. There are a couple taps here that can allow us to actually change the number of windings on the transformer to also adjust the voltage. That power comes in from the utility into my main winding. It produces a huge magnetic field that flows through the core, through the steel, past the magnetic shunt into the secondary windings. One of those secondary windings is connected to the big capacitor inside of the power supply. That secondary winding, that shunt, and that capacitor form my voltage regulation circuit. It has two taps on it to provide a 63 or 89 volt output. And then the other winding, like I said, is pushing voltage into the charger to charge the batteries. If there's a problem with the utility, the brain of the power supply will see that. It will open up the line isolation relay, activate or I should say engage the batteries. We'll take the DC voltage from the batteries, run it into the inverter. The devices we call MOSFETs will convert the DC to AC. That AC will be pushed into the transformer kind of backwards. So we'll go into this smaller winding. We'll use that smaller winding to produce a magnetic field to induce a voltage into the secondary winding that will step the voltage up from 26 volts, for example, up to 89 volts. The magnetic field does flow to the winding on the top, but because we opened up the line isolation relay, energy does not flow back out of the power supply. All right, so not really the power supply, but what is the purpose of the SPI? So some people call this the alt box, the alt can, alt switch, a lot of different names for it. We call it the service power interface. What's the purpose of this device? This is the device that interfaces between the power supply and your coaxial plant. You've got Anderson connectors here that would be hooked up to the power supply, and then on the back side of the SPI is going to be the coaxial connection. So that's the main purpose of this. What's the secondary purpose? What's this funny connector on it here for, and what's the switch for? That is for alternate power. So on the right side of the screen here, I have an older power supply in the cabinet. Maybe it has a problem. It's still functioning, but it needs to be replaced. I don't want to have an outage when I replace it. So I take what's called a service power supply or another power supply, I set it on the cabinet. I power that alternate power supply up with either utility or maybe a generator. I connect from the Jones connector on the SPI to the alternate power source. Once I have this power supply all set up exactly like this one is, I switch the switch from on to alt. I watch the needle on my alternate power supply here and make sure it goes up when I throw that switch. That means it picked up the load of my cable plant. And now my cable plant is operating on this power supply, and I can do anything I want to the one inside the enclosure without having any type of an outage going on. This, on the left-hand side, the normal SPI box should never be hooked up to anything that could provide RF to it. So this should always be hooked up to like a power inserter or only to a power port on an active device. If you send RF back to this device, you're going to have massive ingress and egress issues. The one in the middle here is a little bit different. It's called an SPI RF. It's really used where you don't have a tap close to the power supply. It has the power inserter built into it. You actually do send RF back to this device. The RF is extracted out of this F connector so you can connect it to your transponder. And you still have the Jones connector and the alt switch, but it's on the top, or the, I should say, the toggle switch. So just a little bit different guy. So this one you would actually hook to RF because it has a power inserter built into it, but this one never hook up to anything except a power inserter or a power port. And also check for voltage on these connectors. I've seen weird problems occur before, technicians having a tough time figuring things out, you know, why they're having a problem. And you put your voltmeter on these two cables, these two connectors here, and you show voltage coming back from the cable plant. You should never show voltage coming back from the cable plant, right? If you do, you need to track down where that voltage is coming from and eliminate it. This screen here just kind of shows the entire flow. So high voltage from the power company comes into their transformer. They step it down to a lower voltage. That 120 volt, 60 hertz sine wave goes into the power supply where we convert it to the quasi square wave after we step it down. We also take some of the power and charge the batteries. We push out that quasi square through the SPI onto the coaxial plant. We go into a power inserter. In the power inserter, we mix the AC and the RF together. They won't interfere with each other. They're just different frequencies, right? But we don't always want them together. At an active device, we separate them. The RF goes to the RF board, the AC goes to the power pack, and in the power pack, that's where we convert the AC to DC voltage, which is actually used to power the RF components to increase your RF levels. I have a question here. Is it okay to replace a power inserter with a two-way splitter or directional coupler? If you're using the normal standard SPI, the answer to that is no. If I put a two-way splitter in here in this case, my RF energy from my cable plant is going to flow back to the SPI onto these little wires that go from the SPI to the power supply into my transformer, none of which are shielded, and I'm going to have a massive ingress and egress issue. So know your power supply. You know, what is the input voltage, 120 or 240? So power supplies can be either or. So you should always know, you know, what's your voltage for the input. What's the output supposed to be set at? So you might have power supply that can do 60, 75, 87, or 89 volts. You don't want to have a power supply that is running the plants at 60 volts go bad, and you go out there and stick one in that's set up for 89 volts. You're going to burn up active devices if you do that. So make sure you know what your output voltage is supposed to be. What's the maximum current for my power supply? 3, 8, 10, 15, 18, 22, 24. There are others I don't have on here. But again, if I have an 18 amp power supply out there loaded up to, let's say, 16 amps, and it goes bad, I can't go out there and put a 15 amp power supply into it. It's going to overload the power supply. My inverter, is it a 36 volt or 48? Or I should have had on here, I don't have it, is it a 12 volt? Some inverters are only 12 volts. What happens to my power supply when there's a short on the cable plant? Does it go into foldback? Does it start to cycle? Do I have fuses? Do the fuses blow? What is the battery charger supposed to be set to? Am I using wet cell batteries, gel cell batteries, AGM batteries? How often does it do a self-test? And when does it do a self-test? So it's a good idea to understand this stuff so that when you are installing the power supply or replacing the power supply, you're putting in the one that is going to actually function properly for your plant design. Input voltage, you know, is it 120 or 240? So I have a couple 120 volt outlets here. One of them is a 15 amp. One of them is a 20 amp. You can tell the difference because a 20 amp is always going to have the little kind of sideways T, right, for the neutral. Or is it 240 volts? So on my 120 volt circuits, I'm always going to have a hot, a neutral, and a ground. On my 240s, I'm generally going to have two hots and a ground, no neutral. Why are the cords different? Well, this cord here is connected to a device that has potential to draw more than 15 amps. So if it's a device that can potentially draw more than 15 amps, I really don't want to plug it into a 15 amp outlet because I could overload that outlet. So don't twist the plugs to make them fit into the receptacle. You know, if you have the wrong plug for the wrong receptacle, get a temporary adapter, but also be careful. I have had technician in the past who twisted a 120 volt plug to make it fit into a 240 volt outlet. And that's not a good thing. If you want to check polarity on a 120 volt outlet, take your voltmeter, set up for AC voltage, put a probe in the neutral, put a probe in the ground. From neutral to ground, there should be no difference in potential. It should be 0 volts. If you have any voltage there, that's a problem. If you have approximately 120 volts from neutral to ground, somebody has reversed the polarity, and that should be fixed. Don't work on the wires on the backside of an outlet unless you have been trained and authorized to do so by your supervisor. Breakers. So we recommend that you use high magnetic circuit breakers on the utility side. Power supplies have what's called inrush current associated with them. So when they first come on, they have to basically instantaneously saturate the core with magnetic flux and instantaneously charge the capacitor. To do so, they might draw in as much as 400 amps of current in the first half cycle of that waveform from the utility. If you're not using high magnetic circuit breakers, they're going to trip more often than you want them to. So if you have, utility circuit breakers out there on your power supplies that tend to be tripping more often than not, check them to see if they're high magnetic. Again, this is high voltage. So unless you are trained or and authorized to work on this by your supervisor, don't. Surge suppressors. So some guys maybe see these little guys here and they're not sure what they're for. I've had a lot of guys think they were different things. One guy just saw it. He thought, well, I plugged it in to see if the outlet's actually working. If the green light comes on, it means the outlet's good. Well, that is true. The green lights should be on these. If the green lights aren't on, they're not functional. But these are surge suppressors. They help protect the power supply from the utility surges. Inside of these, we use metal oxide varistors, MOVs. Okay, so basically, you plug these into the same outlet where you plug the power supply in. If you're using the type that has the pass-through, you do not have to plug the power supply into the surge protector, just have it plugged into the receptacle. And when a surge comes from the utility, like this transient here, the MOVs inside of this device will redirect that surge to ground and dissipate it before it goes into the power supply. If the green lights are not working on these, if they're off, take it out, throw it away, put a new one in. Input voltage, again, on your power supplies, there's going to be a little label that will tell you what the input voltage is. This is really important, especially for the newer power supplies that have cords that can be taken off. So some of the newer power supplies, the cords actually come off the power supply. And one of the unfortunate things is that where they plug into the power supply, they are the same. So what can potentially happen is you put the wrong cord on a power supply. And this one here, I have a 240 volt power supply. Somebody's put a 120 volt cord on it and plugged it into a 120 volt outlet. Now, what's going to happen when you do that is you're going to get an input failure alarm, because remember, this power supply is looking for a minimum of 173 volts, and you're only giving it 120. So it's going to believe that there was a failure of the input. Also, if you have the batteries connected to this power supply and they are good, it is going to switch the batteries, because remember when I told you that the input is too low coming in, the brain, which is powered by the batteries, is going to switch the power supply from running on commercial power to running on the batteries. And eventually this power supply in this case is going to run on the batteries till it draws them down to what we call end of discharge. The good thing is I've never seen a 240 volt power supply plugged into 120 volt outlet get damaged. Okay, so if you do that, at least the power supply doesn't get damaged. Now, if you have a 120 volt power supply and you plug it into 240 volts, I can guarantee you that you're going to damage the power supply. You're not going to get any alarms. You're going to see a bright flash and some flames and smoke. So make sure that you check your input voltage and make sure you use the right cord. So different parts of the power supply. We have the transformer module, which is the main part of the power supply. So it's kind of in this square to the left, but it's also behind the inverter and the communications module. So those are the other two. So generally there are really three modules that consist of the the power supply. Again, I have that transponder. Sorry, that's incorrect. That should be transformer module, inverter module, and communications module. The transformer module, which again, I have a typo. The transformer module is where you have the AC input. You have the ferroresonant transformer. You have the oil capacitor, which is this big silver thing. So here's my big steel block. So I have a question here. Why is the power supply so heavy? Well, I have a great big steel block in there surrounded by a bunch of copper. Now, in this case, the copper is covered with wax paper because, again, I don't want the copper wires to be touching the steel. And then I have my big capacitor in here also. I have a power distribution board. The line isolation relay. Remember that relay that disconnects the power supply from the utility? It is actually on the power distribution board. And then you have your outputs going to your cable plant, which I don't show on this picture now. If the capacitor fails, the output will drop dramatically when operating in line mode. So if this big capacitor inside of a power supply fails, when the power supply is running in line mode, running off commercial power, you will see the output drop dramatically. On an older power supply, you might see the output go from 87 volts down to 60 volts. On a newer power supply, generally it'll go from 89 volts down to around 74 volts. Okay, so if you see your output voltage drop dramatically when the power supplies are off commercial power, it's probably because the capacitor has failed, gone out. I have a note down here. Don't access the components inside the power supply unless you are authorized by your supervisor. And if you are accessing anything inside of here, like I have it open, always have all power off to the power supply. Never have the power on when you're accessing anything inside of it. I must have cut and pasted that error all the time. The transformer module, it should say, you want to try to match the transformer to your plant load. So ferroresonant transformers are more efficient when they run at a higher load. Ideally, you want to run at about 85%. You don't want to run all the way up to 100% because you want to leave headroom for plant changes, temperature changes, and so forth. If I'm running my 18 amp power supply at 18 amps, I have no room for changes in my plant. And when I go over that 18 amps, it's going to cause my power supply to shut down. You don't want to run less than 10%. Down here, they are really inefficient. Kind of makes the power supply work harder. And if you get way too low, you might actually have the power supply drop its output until you apply a load to it. So don't run them way down at the bottom, but also don't run them way up at 100%. The inverter module. So the inverter module has my AC detect circuit, so it has my brains in it, which again are powered by the batteries. It has the battery charger in it. So if you get a battery charger alarm on your smart display, that basically means you need to replace the inverter. It also is the inverter, of course. It's the device that changes the DC voltage to AC voltage when we're operating off the batteries. And it has my smart display within it. So a couple questions I have here. What is the purpose of the temp probe? So I have a temp probe connection here. The temp probe is really important. The temp probe connects from the inverter, which is the charger, down to the batteries. And we will adjust the battery charge voltage based on the temperature of the batteries. So it's important that you use the correct temp probe for your power supply and that it is properly placed on the batteries. My question down the bottom, why should you set up the charger to match the batteries? So most power supplies will allow you to go into the smart display and actually select the battery type or manually set up the battery type in the smart display. And what that does is it optimizes the charger so that the charger and the batteries match, and that will help keep your batteries from overcharging or undercharging, which will make the batteries last longer over time. I also have a note over here too. Make sure the battery breaker is off and the battery cables are disconnected when you are removing or you're installing the inverter. So don't have the batteries connected to the inverter when you're pulling it in or pushing, or when you're pulling it out or pushing it in. The smart display. So some smart displays go inactive when you're not using them. You have to push the button to start them up. but it's really important that you understand how your smart display works. So, look at the manual or push the buttons. I have a couple questions here. Can you turn off the power supply by pushing the button? I don't know of a power supply that pushing buttons will ever shut it off. So, if you're pushing buttons to see what things will do, it's highly, highly unlikely that you're ever going to shut the power supply off. Can you change the output voltage by pushing buttons? I've not seen a power supply where you can actually change the output voltage by pushing buttons. So, pushing buttons to learn is not a bad thing. I mean, ideally, you want to look at the manual or get somebody who understands the smart display and have them do a little training for you. But I got to admit, one of the ways I learned how to run devices is pushing the buttons and see what happens. Transponder. So I finally got my thing up here correct. So the transponder module. That's your communications module over to the right-hand side here, right? It's a DOCSIS modem. Some of the newer ones have SFP sockets in them. And generally what the transponder is being used for is remote status monitoring. Like I said, it's a DOCSIS modem, so it's going to be hooked up to RF. Ideally, you're going to have a surge protector with a bond block. You're going to ground that to the cabinet, and then you're going to make sure your RF levels are correct for your receive and transmit for the DOCSIS modem that is in your transponder. Generally, nowadays, they're probably going to be DOCSIS 3 or DOCSIS 3.1. There is a web interface or a GUI that you can get to by connecting a laptop to the power supply Ethernet port on pretty much all power supplies that I know of. So I connect my laptop using an Ethernet cable, a straight cable. I go into a browser, I type in 192.168.100.1. That should log me into the power supply's interface. Now, there are some companies that shut off that interface so that there is not access to it. So if you can't get to that, it may be because your company shut off that interface. Some companies allow technicians to remotely access that GUI interface. So, if you have access to the GUI, utilize it. There's a lot of information you can get by logging into the power supply. Use your status monitoring system, but your status monitoring system does not give you all the information. The GUI, the web interface will give that all to you.
If I may pause for a minute before we get too far along, I want to launch the third question. We'll skip the second one for now. So here we go, folks. So the question is, when tested in an open circuit, ideally, what should a fully charged 12-volt battery measure? See, well, we have some responses already. I'll go on mute. I'll give it a minute here, so let everybody get a chance to vote here.
And Woody, I apologize. I always put too much information in my presentations. I'm probably going to speed up a little bit because I have a lot to go through, and I apologize for that. But those who are listening in, again, if you have questions, please type in the chat so Woody can ask those to me.
So we've got 72% voted. That's a pretty good number. I'm going to close the poll. And let's see, well, we got 80%, so a highly interactive group today. Okay, and then I'm going to share this. So 10% said 11.8, 20% said 12, 5% 10.5, and 65% 12.8. And I do believe that is the right answer, correct, George?
So the correct answer, a fully charged 12-volt battery with no charger on it and no load applied to it should measure about 12.8 volts DC. 12 volts, 12.0 is only about 40% charged. 11.8 is well, I shouldn't say way too low. And 10.5 is basically what a battery will be at when it is at what's called end of discharge, when you can no longer get any voltage out of that battery. So I'll go over this a little bit more detail a little bit later, but remember, a fully charged battery should be about 12.8 volts. Some batteries, and I'm talking about an AGM battery there. Some of the other older batteries, it was about 12.6. So, 12.6 to 12.8 is ideally where you want to see your batteries when they're fully charged in an open circuit, meaning not connected to a charger and not connected to a load.
So thank you everybody for answering that, and thank you, George, for clarifying. We'll move along.
So I'll go through this kind of quick because most of you guys probably know this, but how do I troubleshoot my transponder? Well, remember your transponder is a modem. So troubleshoot it basically like a modem. One thing your modem may not have, of course, is alarms, but you can look at your alarms on the power supply. Make sure the transponder is powered up. Are the little lights lit up on it? Maybe when somebody put it in, they didn't match up the pins between the transponder and the inverter. Maybe they don't have things hooked up right. But is it powered? Are your RF levels correct? It's a modem. Treat it like a modem as far as RF. Is it provisioned correctly? You might have to get involved with your NOC or your IT department or somebody like that to make sure that they got the right MAC address, that it's pulling the correct IP, but check with provisioning. So, you check it, it's powered up, the RF levels are good, provisioning says it's good. Don't forget to reboot it. It's a modem, right? A lot of guys forget to try a reboot. So how do you reboot the modem in your power supply? Well, you have to power the transponder down. And the way to power the transponder down is to shut off the battery breaker, disengage the battery cables, loosen the thumb screws, pull the inverter out until the lights on the transponder go off, and then re-engage it and hook it back up. If you do, steps 1 through 5 and it still doesn't come on, well, I'm sorry, it is a modem and modems do fail, so you may have to replace it. And of course, you can always call technical support to, ask for help also. I mentioned that some power supplies have SFP sockets on them now so that you can monitor the power supply with the optical network. A lot of places we're doing remote OLTs. We're doing basically fiber to the home, still using the power supply to power a fiber device. Well, if you don't have any RF close by, you can't use the DOCSIS modem to monitor the power supply. So you use maybe an SFP with an ONU built into it that you plug into the SFP socket on the power supply. Couple alarms that I want to stress. Self-test fail. So a self-test is performed by your power supply periodically. From the factory, from the company I work for, it's every 30 days for 10 minutes. So every 30 days, we are going to disconnect the power supply from the utility. The power supply does it itself, you don't have to, and it tries to run the batteries for 10 minutes. If it can't do that, or it starts the test and it can't make the full 10 minutes, it's going to fail the test and you're going to get self-test fail. That's an important alarm. That means that your power supply is either not going to run on the batteries or it's going to run for a very short amount of time. The main fail or the main reason for a self-test fail generally is bad batteries. I would say that's probably 80% of the time is what I see. But there are some other things that can cause a failure. The inverter overheating, voltage being lost during the self-test on the utility side, a short circuit on your plant during the self-test, or the line isolation relay not functioning. If you get a self-test fail in your power supply, you need to fix the problem and then run a manual self-test on your power supply. And if you fix the problem, once you run the manual self-test and it completes, the alarm will go away. Line isolation, we talked about that earlier. That's the little relay that disconnects the power supply from the utility. Every time we turn on the batteries, if we can't open that relay for some reason, you're going to get a line isolation alarm. And when you get a line isolation alarm, it means two things. One, the power supply won't turn on the batteries. It'll run on the utility power, it just won't run on the batteries. And two, the only fix for a line isolation relay alarm is to replace the power supply. There are other alarms. I'm going to kind of skip through most of these just because of time. But if you need to, if you want to see all the alarms in your power supply, you can go to the manufacturer's manual, and they'll generally be listed in there. One I do want to note is a MOV fail. Metal oxide varistor, that's surge protectors. So some of the newer power supplies will tell you when the surge protectors that are within the power supply have failed and need to be replaced. Batteries. So let's talk about batteries for a bit. So batteries can be dangerous, okay? Batteries are low voltage, but again, that doesn't mean that they're safe. There is no safe voltage to work with. But batteries have a huge amount of stored potential within them. Always follow your company's safety policies. Use the PPE required by your company when working with batteries. Ideally, you want to remove your rings, your watches, your necklaces, any metal items. Have respect for the batteries. Again, low voltage but high current. If you drop something on the battery, like I'm showing my wrench dropped on there, do not try to grab the wrench and pull it off. Back away from the batteries if you drop something on there. If it starts sparking and flashing, stay away from it. Once it stops sparking and flashing, then use proper PPE and gear to remove what you've dropped on the batteries. It is possible that when batteries are short-circuited, like this one hits here where the wrenches touch the positive and the negative, that's a short circuit. You can have an arc flash. You can actually have very high heat produced. It's possible even for the battery to explode. Question I have here, what is meant by string voltage? Well, string voltage is the total voltage of the string. In this case, my string is 3 batteries connected together. So I can check string voltage in 2 different locations. One is I could go from the negative of my number 1 battery over here on the right to the positive of the number 3 battery with a voltmeter, and that would give me my total voltage. Or I take my connector out of the power supply inverter and I test from the positive to the negative on that connector. That would be my string voltage. Always test your batteries. I get calls from technicians all over the country. I just honestly, the reason I kind of stressing this, I just got a call from a technician a couple days ago, and when I asked him what the voltage was on his batteries, he told me, George, I just got them out of the warehouse. That doesn't mean they're good. And in his case, they weren't. So always test your batteries. Like we mentioned in the survey earlier, when fully charged with no charge or load applied, a valve-regulated lead-acid AGM battery will ideally measure 12.8 volts. So you can see my first battery here is 12.8 volts. My second battery, 10.72. Well, that's not good. It's recommended that if you have less than 11.8 volts on your batteries, don't connect them to the power supply. So in that case, I'd want to replace that battery, put a new battery in there, and now it measures 12.62, which isn't 12.8, but it's definitely above 11.8. And then my third battery is 12.57, again, not 12.8, but still above the 11.8 threshold. If you're going to work on the batteries, so if you're going to put a wrench on the terminals or put something on the terminals besides test gear, shut the breaker off, disconnect the batteries from the power supply. When the power supply is running off the batteries, it's actually, again, we're taking the DC, converting it to AC. Use the correct temp probe to ensure that it is properly placed. Again, what the temperature probe does is it adjusts the voltage going into the batteries. The colder it is, the more voltage we put on the batteries. The hotter it is, the less voltage we put on the batteries. And then, very important, heat kills batteries. Don't squish those batteries together. Space them apart as far as you can to allow for air to flow around the batteries. Again, I get out in the field a lot of times, I see the batteries all smashed together and they're wondering why they're failing prematurely. Heat is really bad for batteries. Woody, do you want to throw up that last survey question? Did I lose Woody?
No, I'm still here. Sorry about that. Took me a second to get off mute. So yes, I should have asked the other question later, but here we go. This will be the final survey question.
That's all right.
And let's see here. So you should all see it now. As the outside temperature goes down, what will the battery charger do? Remember that we talked about the temp probe earlier, right? And it's going to sense that the temperature has dropped. So and then it will trigger response from the charger. So what is the charger going to do? So we have 20% voted. I'm going to go on mute, give it a minute, and be right back.
All right.
So we're up to 64%. I'll give it just a few more seconds and we'll stop it and read out the correct answer for everybody.
All right.
Okay, we will stop there. I will close it and share the response. So looks like the vast majority of folks got this right. I wouldn't say vast majority, I shouldn't say that, but it's like about half got right. So the correct answer will be it will increase the battery charge voltage. Would you like to?
Batteries get cold. Yeah, as batteries get cold, we have to increase the amount of voltage we put into them to force that chemical reaction to occur to move those electrons from one lead plate to the other lead plate. As the temperatures get hotter, we don't have to put as much voltage on the batteries to charge them. So the colder it is, the more voltage. The hotter it is, the less voltage.
And just
the one there,
comment on that, George.
yes.
I do believe, I'm not sure with the glass mat batteries, but with the lead acid batteries used to deal with a long time ago, they had less output power when they were cold. Is that still the case?
Can still happen. So yeah, what happens when the batteries are cold is the chemical reaction doesn't work as well. So yeah, the amount of energy that you get out of those batteries can be reduced.
So not only can you increase the charge voltage, but by increasing the charge voltage, you create more heat, so it makes the batteries more efficient should the power supply go into standby. Is that correct?
Yeah, kind of. The other thing too I see is somebody said had 5% said turn on the power supply heater to warm up the batteries. You know what? I didn't think about that when I put that. So there is no power supply heater, but maybe you've worked with these in the past too, but up north, we used to actually put heater mats under the batteries to warm the batteries up in the winter so that they would produce energy. So the power supply itself doesn't have a heater, but we actually did used to put heater mats underneath the batteries to keep them warm in the cold of the winter. When I used to work in Minot, North Dakota, where it was, I think today it's probably minus 40 in Minot. Those batteries are not working extremely well up there just because of how cold it is.
Thank you, George.
Yep. All right, so I kind of mentioned this already, string voltage. So you want to measure your string voltage. If you measure your string voltage and it is incorrect, then measure, of course, your in this case, I've gone out to a power supply. I haven't measured the individual voltage. Yes, I measured the string voltage. If it wasn't where I think it should be, then I would start testing each individual battery. I do want to note that some newer power supplies, if the string voltage drops below 33 volts, the power supply might not recognize the batteries. So again, I had a gentleman contact me the other day. He told me the batteries were new from the warehouse. Well, when he finally tested those batteries, when he finally tested the string voltage on the batteries, he only had 31 volts. And he was getting a no battery alarm on his power supply and a string A miswire. When he tested the individual batteries, one of his individual batteries was down to like 10.8 volts. So he had one battery from the warehouse that was actually bad. You can do a float voltage test with your voltmeter. You can some power supplies actually will let you see the individual battery voltage on the screen too. So instead of using your voltmeter, you might be able to do it just on the power supply. And float, I should have mentioned this earlier too, is to know if your batteries are fully charged, you want to go into the power supply and look at what charge mode they're in. Float means the batteries are fully charged. And ideally, you want to test your batteries when they are fully charged. The conductance meter, I mentioned this earlier. It's an ideal way for testing the batteries. The voltmeter will just tell you if the batteries are charged. It will not tell you if the batteries can carry a load. So I've seen before where you've had good voltage, but as soon as you tried to run on those batteries, the load would drop. That could be an internally shorted cell. It could be a variety of reasons that battery can't carry the load, but it shows good voltage. So if you have access to a conductance meter, I definitely recommend utilizing the conductance meter. And if you don't know how to use this meter, again, talk to your technical training department, engineering department to give you information, or contact me or somebody at my company and we can explain how this meter works for you. I sometimes I get disappointed as I travel around. I went to one location one day. I asked them if they had this meter. They said no. One guy said, he goes, I think we do. And he ran out of the classroom. He comes back in with this box. He says, is this it? I said, yep, that's it. He goes, we got 7 of them sitting on a shelf back there. They had bought 7 of them 3 years ago. Nobody knew what they were or how to use them. So they had been sitting on a shelf. Inverter voltage. So make sure that you have the right batteries connected to your power supply. So I have 2 power supplies here. One is a 36 volt inverter. One is a 12 volt inverter. They both have 3 batteries hooked up to them. Well, how can that be? Well, because of the way the batteries are wired. The batteries in the power supply on the left-hand side are wired in a series. So negative, positive, negative, positive, negative, positive. When you wire batteries in a series, the voltage is additive. So these 3 batteries adds up to 36 volts. On the right side of the screen, that little power supply has a 12 volt inverter. I have 3 batteries hooked up to it, but they're wired in parallel, meaning positive, 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 negative, negative, negative. When I wire batteries in parallel, that means the voltage stays the same. So you don't want to hook up the series wired batteries to that 12 volt inverter because it would damage it. And if you hook up the parallel wired ones to the 36 volt inverter, it's not going to have enough voltage to operate.
I do have a question, George. The question comes from Larry. Which battery powers the embedded modem?
Well, which battery powers the embedded modem? So I'm thinking Larry's probably asking how. So on some of the older power supplies, or maybe not, I shouldn't say older. So on we have a power supply called an XM2, and that XM2 has a transponder called a DM3X. And most of the transponders on power supplies, the modem is actually powered through the interface between the inverter and the transponder. On that particular transponder, the DM3X, we actually power it with the little wires, the little sense harness wires that come from the batteries. Larry, I'll put up my email address later. If you send me an email, I can't remember which pins on that connector actually power the modem. I don't work with XM2s as much as I used to, but if later on, Larry, if you me type in my email in the chat.
What I do remember, and again, this is from the past, but we did have transponders at one point that did get their power from battery number 1. So if battery number 1 went dead, you lost visibility of the power supply. That's been a while, so I don't know if that's still the case anymore.
Yeah, and there are some manufacturers that did power their transponders with the batteries. We did a long time ago too, and like I said, we currently do have one that works that way. And like I said, if Larry sends me an email, I can find out which pin that is. But most of the new transponders and new power supplies, all of our newer stuff, we do not use the battery string to power. We power through the interface between the transponder and the inverter. So how long is my power supply going to run with the batteries? Well, runtime depends on a lot of different things. Transformer efficiency. So older power supplies aren't as efficient as the newer ones. So newer ones tend to give you longer runtimes. The load. Of course, the higher the load, the shorter the runtime. But I can offset that by adding battery strings. The battery type makes a difference. As batteries age, they tend to lose their capacity. They can't hold a charge like they used to. And then we talked about before, is it hot or is it cold? Heat kills batteries. Heat is really bad for batteries. Cold just causes the batteries to not produce energy like they're supposed to, but cold generally doesn't damage the battery like heat does. So you can see my chart here, I've got an example, I have a power supply with a 12 amp load with 3 batteries. I'm going to get a little over 3 hours. If I put 6 batteries, I can basically double my runtime. So you can see the batteries in the center towards the top, they are wired in parallel. I'm sorry, in parallel. So that would be 12 volts coming off that connection. The ones to the right of it, those are wired in series. That would be 36 volts because they're wired in series again. And then down below, the 2 strings wired together are wired in series parallel. So the 3 batteries are wired in series. The 3 batteries are wired in series. And then we parallel the 2 strings together, and that maintains 36 volts. So again, more batteries, more runtime. So this is an extended runtime system that we use out in California. I have 18 batteries connected to this power supply. So how many volts are going to be going into this power supply? Well, remember, this power supply is a 36 volt inverter. It's got to be 36 volts. Well, how do I get 36 volts out of 18 batteries? 3 are wired in series, so the 3 are wired in series, and then actually in this case, we parallel them all together with this little device towards the top of the cabinet called a BIU. So even though I got 18 batteries, I still only have 36 volts going into my power supply. Some battery reminders. Shut off the power supply breaker if working on the battery terminal connections. Set the battery charger to match the batteries. So you really want to match your charger to the battery type you're using. That will optimize the charger for those batteries, extending the life of the batteries. Test the string voltage. Test the individual battery voltages. Test your batteries. That's one of the big things I want to make sure guys understand is test your batteries. Space them apart. Don't slam them together. Make sure you're using the correct temperature probe. Don't mix batteries. So don't use AGMs and wet cells or gel cells. Don't mix those together. You should use the same make and model of battery for the entire string. Clean your terminals and seal them. You don't want corrosion to occur. And then finally, if the batteries aren't good, don't connect them to the power supply. The picture to the left, that was a new XM3.1 power supply that the technician put in, and they hooked these old batteries that had the valves bursted on them and stuff connected to the power supply. And these batteries aren't any good. It's pointless to connect them to the power supply if the batteries aren't any good. Bonding and grounding, when you're out there working on your power supplies, check to see if the bond and ground is in place. If it's not, you may not be responsible or the person to fix that, but report it so that it can get corrected. Your cable plant is an electronic circuit. It needs to be properly grounded or bonded to a ground. And also don't be grabbing ground wires barehanded until you've checked them for foreign voltage, especially if they're not connected. If you have a ground wire that came loose from a ground rod and you grab the ground wire barehanded and it has straight voltage on it, and then you grab the ground rod, it's not going to be a good day for you. Some troubleshooting reminders. Do you have the correct AC input voltage? So, before you maybe call for help, Check to make sure you have the right input. Do you have the correct string voltage? Again, test your batteries, test your batteries, test your batteries. Do you have the correct individual voltages on the batteries? And, is your output voltage correct? So, we say 89 volts, but actually if the power supply is running in what's called course mode, it could be as low as 84 volts if it's in the 90 volt range. So check that stuff out on your power supplies when you're troubleshooting them. And then additional reminders here, kind of went over a lot of this already. So is your charger set up for the batteries? Always test your batteries. Is the transponder set up correctly? Is your receive transmit level correct? I didn't talk much about this, but your enclosures, are they tight and sealed so mice and snakes and stuff can't get into them? Are the vents clear of obstructions and clean so that air can actually flow through the enclosure so the power supplies and the batteries don't overheat? Do you have surge protection in place for the AC? If there are alarms on the power supply, look at them and record them before you start messing with the power supply so that you know what's going on with it. If you start messing around with it, maybe the alarm will go away. Maybe you didn't truly fix it, but for some reason you cleared the alarm. Fix the problem, don't just clear the alarms. I've run into technicians before on older power supplies. If you pull the inverter out and push it back in, the alarm goes away. Oh, well, yeah, you cleared the alarm, but you didn't really fix it. You really need to fix the problems. A reminder on repair tags, as much detail as you can. If you have a power supply that has a line isolation alarm, put that on the repair tag so that when they get it at the repair center, they know what to look for. Check the damage, or check your enclosures for damage. If there's things that you can't fix, report it so somebody can fix it. And then one of the things I used to have my technicians do, this is just, again, a recommendation, is anytime they got done working on a power supply, no matter what they did, I required that they run a self-test. So I'm done working on my power supply. Before I actually leave that site, I run a manual self-test. That will verify that everything is working properly. If the self-test fails, you didn't fix something right, and it needs to be corrected. I'm a little early. I have some other slides, but Woody, actually, I don't really probably, well, you know what? I can go through these slides really quick.
Okay, go ahead.
Yeah, just also so there's my contact information, and also there is a QR code that if you click on that or take a picture with your phone, you'll put my contact information in. So what I want to go through quick, I got 8 minutes here, is what happens to a power supply if it is shorted out. So a short is an overload on the power supply. So, power supply is designed for, let's say, 15 amps. When you have a short on the power supply, you're going to have a lot more than 15 amps on your cable plant, right? But there are other things that can cause power supplies to be overloaded. Temperature changes. As your plant, it changes, the temperature changes, it gets hotter or colder, the current's going to change. Adding too many active devices can overload your power supplies. Temporary cables, you put in a small cable and compared to a large cable, it's going to cause the voltage to drop at a faster rate, which will cause your current to increase. Water and passive devices kind of does the same thing. And then you have shorts. So if I have a power supply that gets shorted out, the first thing that's going to happen is it's going to go into what is called foldback. The power supply is going to protect itself from damage by dropping the output voltage way, way down and raising the output current. Okay, so ferroresonant transponders have this protection called foldback built into them. If a utility power company's transformer gets shorted out and they don't have circuit breaker or a fuse on it, it will basically cause the power supply to blow up. Ours won't. They will go into foldback. So foldback means the voltage goes way down, the current goes way up. 30 seconds after the power supply goes into foldback, the brain in the power supply, which is powered by the batteries, sees that and doesn't like it, and it will actually shut the outputs off. They will go to 0 volts. It will wait 1 minute, then it will try to turn back on. If the problem is still there, it shuts the outputs off for another minute, and it will do that 20 times. After the 20th time of 1 minute off, it will start shutting the power supply off for 30 minutes. So it'll shut the power supply outputs off for 30 minutes. wait 30 minutes, try to turn back on. If the problem is still there, shut them off again for another 30 minutes. If you get out to a power supply and it is overloaded, you don't want it turning on and off by itself. So the way to stop that cycling process is to disconnect the battery cables. First, of course, shut off the breaker, disconnect the battery cables from the inverter, and remember the batteries power the brain. So once you do that, the power supply becomes dumb, okay? And then you can start tracking your problem. So let me go through a little scenario. You do not have to do it like this. There are a lot of different ways to crack shorts and overloads. This is the way that I used to do it. So I have a power supply here and everything is good. I've got good input voltage, a good output voltage, good output current. I have no alarms. Then a problem occurs. Now, if I happen to be there when the problem occurs in this case, and I see the voltage go down to 0 volts and the current go up to 23.6 amps, I am pretty doggone sure that a short just occurred on my cable plant. But remember, 30 seconds after that short occurs, the brain in the power supply is going to shut the outputs off and everything is going to go to 0. Then it's going to wait 1 minute and try to turn back on. And it will do that 20 times. After the 20th time, it's going to do 30-minute cycles. So it'll shut off and wait 30 minutes. If you get out to a power supply and it's in one of those cycles, let's say you get out there and it's 10 minutes into that 30-minute cycle, you identify it as an overload or short to the power supply, you disconnect the output from the power supply is not going to go back to normal operation. It's got to wait 20 minutes before it's actually going to try to turn back on because it's in that 30-minute cycle. Again, you don't want to wait for that cycle to complete, so shut the breaker off, disconnect the battery cables. That will kill the brain. Now, once you kill the brain of the power supply with the short still connected, it's going to go back into what's called foldback, low voltage, high current. Now, when you disconnect the short from the power supply, it should come back to normal operation because you've disconnected the short. You can verify that with your voltmeter or, again, look on the screen. I generally would use my voltmeter to verify it. Okay, now what I would do in this case is I would hook the short back up to my power supply. That's going to kill my power supply because the short isn't fixed, right? Then I would go out to my power inserter, take it out, test for voltage coming from the pin that's coming from the power supply. If I don't have voltage at this point, I know my problem is in between my power inserter and the power supply, because remember, when I disconnected the short from the power supply was fine. So at this point, if I've disconnected my plant and I don't have voltage, my problem is between my power supply and where I'm testing for voltage. If I have good voltage here, I used to use my amp clamp, put my amp clamp on from pin to pin. It says 8.7 amps going down the right side. How do I know if that's right? Well, I have to look at my prints and count my amplifiers and do a rough estimation. So I do that, and that looks probably right. I put my amp clamp on the other side. It says 23 amps going down the left leg. Well, I don't even have to look at my prints, right? 23 amps is way too much. Okay. So once I've identified it's going down that leg, I put the faceplate back in. That's going to kill my power supply. I move down to another point. I take the faceplate out. I test for voltage. If I don't have voltage here, that means I went past it. It's behind me, right? If I do have voltage here, test my current. 4 amps going down this leg, 23 amps going down this leg. Okay? Keep tracking my problem out until I find it. Once I find my problem, fix my problem. Do not forget to go back. Connect your battery cables back up to your inverter and turn the battery breaker back on. And then, like I said, ideally, the last thing I would do is run a self-test. So, again, that's not the only way to track a short. That's one method. There are other methods to use that. You might have one that works as well or maybe even works better. Let me get back. There. So, do you have any other questions from anybody? Or does anybody have any questions?
I'm not seeing any questions, but I would just like to make a comment.
Okay.
for technicians and their leaders both. Yeah, don't guess on things or try to do a process of elimination. Uh, um, Almost all the companies we deal with have technical support lines. George has given out his number here. So if you have any questions or get in a bind, have an outage, most companies, I think you might be the same at EnerSys, actually have people on call. So if you got customers off and you're scratching your head, don't wait, make the phone call.
I do greatly appreciate everybody's time today. I hope you found this presentation to be educational and beneficial to your jobs. If you think that there are some things I should change in it, don't be afraid to send me a little note telling me how I can improve it.
And by the way, we have put a copy, or we will be putting a copy of this presentation on our website, and it's also being recorded. So you can also replay it through sct.org if you didn't have a chance to catch it, or you know somebody else who would like to see it. So thank you everybody for joining. Have a wonderful day.